So this year's question is from the 2015 exam. Type 1, because it's rate and accumulation, this is a yes calculator question. We have a rate of water flowing into a drain pipe, R of t, from time 0 to 8. The pipe's partially blocked, allowing water to drain out the other end at a different rate in cubic feet per hour. There are 30 cubic feet of water in the pipe starting at time 0. Part A says, how many cubic feet of rainwater flow into the pipe? This is a very straightforward, common rate and accumulation question. How many cubic feet flow into? So we are going to integrate the rate function. The rate of into, which is R of t. So we want to integrate R of t from time 0 to time 8. This particular function, 20 sine t squared over 35, probably isn't too easy to do by hand because we have a composite function, and that usually makes it tricky. There might be some substitution tricks and maybe even some integration by parts, but because it's a calculator active question, very easy to do with a calculator. Grab a calculator. Josh was here. Nice, Josh. Bye, Josh. Press math 8. Not math 8, we're integrating math 9. Pulls up the integral command 0 to 8, and then our function 20 sine x squared divided by 35. Double check to make sure you're still in radian mode with the calculator, which we are. If we press enter, we get an answer of 76.570, approximately 76.570 cubic feet. Now, they did not ask for the units, so it's okay if you don't write the units, but that's how much water has flowed into the pipe. You get 2 points, one for the integrand and one for the answer. I guess since they are saying the integrand, maybe they're only interested in, is this what you put inside the integral? So, and then one for the answer. On to part B. Is the amount of water in the pipe increasing or decreasing at time 3? Well, if R of t represents the rate into the pipe, and d of t represents the rate out of the pipe, if R of t is greater than d of t at time 3, then inflow is greater than outflow. Therefore, amount is increasing. Okay. So what we want to do is compare R of 3 to D of 3. R of 3, we grab our calculator and evaluate, and we want to compare it to D of 3. So R of 3, 20 sine of 9/35, 5.0863, and then D of 3 would be negative 0.04 times 27 plus 0.4 times 9 plus 0.96 times 3. 5.4. After evaluating this, we see that this is a false statement, so the true relationship is R of 3 is actually less than D of 3. Therefore, the amount is decreasing, the amount of water, because basically we're getting 5.4 gallons of water exiting the system for every 5.08 that enters the system at time 3. So the amount of water is decreasing. This is worth 2 points. The first point is, are you considering R of 3 and D of 3? And then the second point comes from, can you use that to draw your conclusion? On to part C. At what time between 0 and 8, the amount of water at a minimum? So we need to have an equation that models the amount of water in the pipe, and then we need to minimize that equation. So the amount of water in the pipe is going to be the amount you start with plus your accumulation from time 0 to time t. You accumulate by putting water into the system and removing water out of the system. Okay. So this is your accumulator function that will tell you how much water is in the system at any given time t. Our goal is to minimize this equation, so we're going to start by taking the derivative and then finding the critical values. So a prime of t is equal to r of t minus d of t. In other words, the derivative of 30 is 0, and the derivative of an integral, based off the fundamental theorem of the calculus, is f of the top times the derivative of the top minus f of the bottom times the derivative of the bottom. So we now are able to establish critical values occur when r of t minus d of t is equal to 0. We find critical values at t is approximately 0 and 3.271. And I use my graphing calculator to graph this function and this function into y1 and y2 to calculate the intersections. So we've established our critical values, and we're looking for an absolute extrema. Absolute extrema occur either at endpoints or at critical values. So what we need to do is then evaluate what is a of the 0, a of the endpoint, and a of the critical values that fall within that interval. This is the candidates test. Candidates test. Our candidates for absolute extrema are the endpoints or critical values for the function. A of 0 is how much water was in the system at the start, 30 gallons. A of 8, we'd have to then plug 8 into this equation with our calculators, and that gives us about 48.543 gallons. Oops, I wrote that on the wrong one. 48.543. And then A of 3.271, again, we stick this number back into our A function. With a calculator, that comes out to be about 27.964 gallons. The goal was to find where we had a minimum. Our minimum is right there. So the amount of water is at a minimum of 27.964 gallons at T is approximately 3.271 hours. This is worth 3 points. The first point comes from identifying that you need to find critical values where the R of T is equal to the D of T. The second point is the answer, which is 3.271 hours, and then the justification comes from what we're doing here, which is the candidates test. Okay, and finally part D, the pipe can hold 50 cubic feet of water before overflowing. Well, we've established that the amount of water in the system is 50 plus your accumulation. This represents the amount of water in the system. 30, sorry, 30. Thank you. Starts with 30 in the system. Okay. And the question is to write but do not solve an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. So overflow will happen 0 to W, R of t minus d of t, dt, when that equals 50. There's an equation in terms of W, and if that ever equals 50, then we'll get overflowage. Again, we could have used the variable x here or any variables. I just like to revert back to t when possible. This is worth 2 points. 1, did you have a integral of r minus d? And 2, did you have an equation that looked like that?
Do math.
All right, comment, like, subscribe, hit up Nolan Hahn on Instagram. Make sure you hit the bell so you get notifications.